morning, everybody. Thank you for joining us. Today, I'd like to carry on talking about the software architecture that we looked at last week, and particularly see how that we can implement it within the Keil MDK. So just as a quick recap from last week, we discussed a software architecture that was a layered system based around a small footprint operating system. At the top, we had application-specific threads, which were making calls into the service layer, which is composed of software components. So the bulk of our code is sitting in the surface layer in library-specific components. And these components are isolated from the hardware through a lightweight driver layer that's based on the CMSIS driver specification. So what we have throughout our projects is a set of software components that provide the application functionality that are designed to be independent of both the thread code and the driver layer, so they can easily be reused on future projects. Now, when we adopt this approach, there are a number of features within the tool chain that allow us to improve the quality and the reusability of these software components. So within the tool chain, we can make them easier to configure through wizards and annotations. We can add Doxygen, so we can auto-generate documentation. We can also start to customize the debugger with special component viewer windows that give us a specific view of our component, and also event viewer annotations that will give us the flow of execution and also timing information. If we develop our software component in it's sort of isolated mode, we can more easily test it. So any test projects that we create, we can reuse these as bring up projects in future designs. We can bundle all of this together to place it in a CMSIS pack so that it can be installed into the tool chain and then very easily reused and maintained for future projects. And when it's in a pack, we can also add code templates and also examples to help other developers as they go along. So here we have our software component. We make sure we isolate it from the hardware through using the CMSIS standards. So the CMSIS RTOS, which gives us the standard API for small footprint operating system. CMSIS Core, which provides standard functions for talking to all of the registers within the Cortex processor. And CMSIS Driver, that gives us an abstraction layer to talk to the hardware. So if we use these standards, our software component can be easily ported onto any other device that we're going to use in the future. Now, to look at how we can adapt it, we can start to add configuration wizards. So these are typically put in header files so that any of the hash defines in the project are made available for configuration through a GUI type interface. So here we have a custom component, which is a GPS library. We've got a pick list so we can decide which of the NMEA sentences that we're going to use. We can also specify the UART that we're going to use as well. And since we're using a CMSIS UART driver, we can use the CMSIS names. So this means that the code is still portable for any other device. And again, we can specify the baud rate as well. So we can create these configuration wizards simply by, first of all, adding the header that says we're about to start defining the configuration wizard, and then the end of it. And then any of the hash defines that are in our code can be added to our configuration wizard through simple annotations or XML tags placed in the comments within the header file. So here we're providing the pick list for the UART, So we specify the UART names. When we make a selection, that value is then pushed into the hash define underneath. So these are very quick and easy to do. Once you've done it once, it's kind of a bit of cut and paste and modify. So you can build up future menus very, very quickly. So there isn't actually a lot of overhead in doing it. But when you come back to the code or you come to somebody else's code that's using this, it's much more intuitive to configure. You can see the groups of hash defines, etc. So all this is defined in the CMSIS pack documentation. So although this is supported in the MDK, it is a CMSIS standard, so you should be able to use it on other tool chains as well. Now we talk about the component layer. This is going to talk to the CMSIS driver layer. So this provides a set of low-level drivers for common peripherals on a Cortex-M microcontroller. So these are typically communication peripherals. They're originally developed so that CMSIS drivers would be the target for third-party middleware. So everybody wouldn't have to keep reinventing the wheel. So we can take advantage of that and start to use these drivers that are provided as part of the device family pack. So when you install support for a microcontroller, ideally you should also get a complete set of supporting CMSIS drivers as well. So we can then add to those to our project, and from there we have a fairly standard user API for them. So here we can, for example, call initialize. So this will configure the GPIO and install a callback function. We've then got a main control function that we can use to set up the peripheral, and then we may have some custom functions to actually use that peripheral. So in a typical application here, we can add support for a UART. So again, we're initializing, installing the callback function, switching the device on, configuring the UART options, enabling transmit and receive, and then we have separate send and receive functions. So when we receive a message, it triggers the callback, which we can wait for a signal, and then we can receive that data and read it. So once you've learned this, it's pretty straightforward to use, but it will be the same for every microcontroller. So any code that's within our software component that's using the CMSIS driver API is very portable across lots and lots of devices. It means you don't have to spend lots of time writing and bringing up low-level drivers. You can use a CMSIS driver. If it doesn't have the features, there's nothing to stop you developing a more custom specific driver. The CMSIS drivers also come with a validation framework as well. So we can add this as a pack. We can select the drivers that we're using. And then we add a simple line of code, so call the driver validation framework. This will then execute a set of tests that we define, and this will then give us pass or fail tests for our driver layer. So within the tool chain, we can simply select the CMSIS drivers we want, add them to our project, bring up the test framework, and then we can validate the driver layer very, very quickly. That's probably less than a morning's work. It also works very well as a board bring up framework as well. So when you have new hardware, we can use the test framework to validate both the driver and also loopback functions, etc., on the hardware. So we can then get results which are either plain text or HTML, and we can store those as part of our documentation as well. So this is a very good way of bringing up a device initially. One of the problems that we have for our overall architecture is that the CMSIS driver profile doesn't cover a lot of the on-chip peripherals, things like ADCs and timers and DACs, etc. So here we can create our own custom driver profile. So it's up to us how we design it, but we can follow the CMSIS driver framework to keep that style. And we can also add tests to the validation framework so that we can bring up and test our driver. The CMSIS driver framework, we'll have a look at it in a moment, but it's pretty much a skeleton framework, so that it doesn't add a lot of overhead to our code. And once we've done the initial profile, we can create a template so that we're not spending a lot of extra time writing complex CMSIS drivers. And if we're defining our own driver, we can make it a bit simpler than the standard drivers, so we can populate the code more quickly. So typically here, we've done one as an example for a timer. Here we're specifying the timer that we're going to use, and we're following a very similar API that we saw on the UART. We're initializing, installing the callback function for the interrupts, switching it on, configuring the timer, and then configuring a compare channel. And then we can start the timer, and then we'll get a periodic timer with a capture compare channel. Now, when we set this up, this is quite a lightweight framework. So for each of our timers, we define a structure with its collection of functions that we're going to have. We can then define each of those functions. So for timer 0, for timer 1, for timer 2, etc. So we can call that function, for example, to initialize. We then call inside this function a base function, so timer X, and we pass a resources structure to that as well. So this provides all the configuration information for our specific timer. So in this case, timer 0. So then in our base function, when we pass in the resources, here we're saying the base address and interrupt channel of the timer, and we're also giving it the pin configuration and the specific pins as well. Okay, so we're just providing this low-level information so we can set up our driver. And then inside the code, when we pass the resources in, that information here, for example, is ready to set up the GPIO pins. And here we're installing the callback function into the information structure as well. So this is quite a light framework. It's essentially a code-only framework, so we're not having any local data in here, so we can instantiate this multiple times for a number of timers. So you do the code once, and then you can use it for all of the timers that have the same structure within your device. We can also add to the test framework as well, so we can extend the driver framework quite easily. So we can provide a lot of tests for our timer. So then as soon as we've developed it, we can validate it and also use it on board bring up as well. Within the pack system, there are a number of general purpose packs that we can use across all microcontrollers. And one of those generic packs is a software testing framework called Unity. So this allows you to write developer tests within your code. And those tests can be hooked up to the instrumentation trace, or as we'll see later, the event viewer that will connect to a console window directly into the debugger. So you don't need to use any any additional hardware on the chip, so like a UART for a test interface, for example. Unity will also, as I say, work down on the hardware, but there are a number of simulators that are included with MDK as well. And since our component is source code only, or C code only, it doesn't touch the microcontroller hardware, we can test it or provide first level of testing within a CPU simulator. And indeed, for smaller devices, that's quite a big advantage, because if we're testing on an M0, we can very quickly run into memory problems because the device doesn't have a lot of memory. If we run it on a simulator, we can add in extra memory for the test framework to prove our basic code, and then we can try and do some more testing down on the hardware. So simulation is quite useful for software testing. Within Unity, we have a main framework, which we can then define test groups. And within the test group, we have setup and tear down functions, so we can configure our microcontroller for the code that we're going to test. And then in a test group, we can define multiple tests. So here we're copying a test sentence into our GPS buffer. We're then calling a function to parse that buffer to extract the information and generate and put values of lat and long and time, etc., into a structure that we can use. We're then using the asserts within Unity to look at the results we get from our function and check that we got the correct values. So this is very quick and easy to set up. And as you're writing code, you can be developing tests to make sure that everything's functioning correctly. And then, of course, those test frameworks can be reused on later projects, again, to validate the component when we've installed it onto a new device. So typically we can have a main application. So in here, we've got our GPS code that is running as a component, and we'll talk to our application code. But for testing, we can create a separate project. We can add our test framework, so this gives us a complete execution environment. And then we can add in our test code, and we can run all of our tests within this sub project before we migrate it into the application framework. And indeed, these test frameworks can become development frameworks. So it allows us to write the GPS code in isolation and build up its framework as we go along before we migrate it into the validation. So we have an approach of adding these developer test code, which is not a substitute for unit tests, but it does give us more confidence that our code is working before we put it into the full application. So when we're working with this style of framework, building our project as a set of sub-projects and then integrating the components together gives us a very nice way to work. So at the bottom level, we've got a test framework for all of the CMSIS drivers. We create these sub-projects for each of our components, add the test code, and when we're happy, we can start to add it together with the application threads to build up the full application. And each of these points provides us a very good test interface so that as we go along, we build more and more confidence in the code so that we can build a working application later on. As we're designing our components within the debugger, we can extend the debugger interface to provide us a deeper view of our software component. And this is very useful to do on any project, but if we're going to reuse the code, any effort that we spend here will save us a lot of time on future projects. So there's two main things that we can do. There's a system within the debugger called a component viewer, and this allows us to look at global data values that are in our code, and then provide a custom watch window that breaks out that data into meaningful values. So here we're for example, looking at a file system, and we can see the current state of the file system. Here we're looking at the USB, and we're breaking out bit fields into text fields so we can see exactly how the component is working. So it's quite easy to develop these for yourself. It's again another XML file which we then add into the project. We also have an event viewer. So this is kind of like printf style debugging, so that we can annotate our code and then it will send up runtime information as the code executes to the debugger. So we build up a list, sort of an application trace of how our code is executing. And again, time spent on both of these provides you a lot of extra detail and information when you go to debugging. Also within the component viewer, it's possible to set alarms so that if a variable goes above a certain level, it'll instantly show you within the debugger. So again, you can get a good feel for how your component's running at any point. So we designed those, both the event recorder and the component viewer as an XML file. So these can then be loaded into the debugger and then become available as part of the watch window. So here, when we're using the operating system, for example, there's a dedicated component viewer for the RTOS. So open that and we then have a deep view of the operating system. The event recorder is a little bit different. Here, we add a small agent to our code, the event recorder code, and this creates a small memory buffer on board the chip. And again, we've got control of the size of this. We can then add annotations to our code. So rather than printfing through a UART, which is quite slow, when we hit an annotation, it will write a few bytes into the event buffer, and then the debugger will connect and non-intrusively upload that data into the debugger, where it can be displayed as a trace window. So we're taking a little bit of runtime, but the minimum runtime to write into this event buffer, and then we're able to see a lot of our application activity within the chip. So now we get this runtime trace, so we can get the component that's sent us the information, some information about the event, and we can also send current values of data as well. And we also get timing information here as well. So the more of these event recorder annotations you add, again, a deeper and deeper runtime view you get of your code. There's a lot of filtering built in as well. So again, if we structure the event message, we can start to filter things out. So we can set the filter at a number of levels and cut out and just see sort of, for example, errors, or get full range of information events about what's going on in our code. There's also a slightly different event annotation as well. So this is for runtime measurement. So we can start and stop time measurement between events as well. And then we have a slightly different window that will give us min, max, and average run times. If we're using the ULink Plus, that can do power measurement. So in here, you can get the energy requirement for different regions of your code as well. So again, we can optimize on time, and we can also look around for energy hungry areas of the code and optimize those. Again, if we're developing a component for reuse, this means that we can also start to characterize it as well. So we can get an idea of its, from the compiler, we'll get its code and RAM usage. But here we can also start to looking at its runtime performance as well. So when we're starting on a new project, we know what components we're going to use, we know what resources they're going to use, and that will guide us in selecting a device. So again, the more we start to think about the architecture and code reuse, the more benefit we get from that system. Also within our documentation, we have a well-defined API which we use to call our component, and if we add the annotations in from Doxygen, we then get pretty much self-documenting code. And we can maintain this simply by maintaining the headers within the source code. So there's the source code really does become the central point of documentation for our project. Now, once we've generated all of those things, we can start to create a software pack. Now, originally, a software pack was intended as a means of delivering support for specific microcontroller families. So it has things like the flash algorithms, the startup code, documentation, etc., the specific debugger windows. But it's also used for a number of other things. So deploying things like the CMSIS standards, other software middleware components, board support packages. But as I say, we can quite easily take any code that we want to reuse and bundle that into a software pack so it can be installed into our tool chain. And this is quite a straightforward process. So the most important thing at the beginning is design our code for reuse. So we can easily extract it from a project and it can be added to future projects. So following the rules that we discussed last week for generating components, if we follow that, we can then add them to packs quite easily. And to create a pack, we simply design a set of folders where we add in the software, the components, the documentation, the XML files that we want to reuse. And then we create a pack description file that tells us about the contents and also any rules for their use as well. There's then a little pack check utility. So this is used to reconcile the XML data against the files that are in the file structure. If that's all okay, we can then zip down the pack, rename it as a .pack, and it's ready to go. So, and sorry, the XML file is included at the top level of the pack. And that XML file, again, is pretty straightforward. There are templates, so it has a number of containers. So first of all, we can define the software components that we're going to reuse. We can specify rules for their use, so we can specify the dependencies. And then there are other containers for things like board support packages. If we have examples of how our components should be used, we can include those. And we can also specify the range of devices that they can be used on. So this can be specific microcontroller families if we want to limit it, or specific Cortex-M processors. It's also with the component when the pack is installed will be visible within the runtime environment. So this has a number of standard trees where we can add things, but if we want to, we can create our own additional branch. So we can have here our reusable components, and inside here is our GPS module. If we go down a bit further, we can then select it, tick the box, and it will be added to our project. And as I mentioned, there are rules. So when we add a component, we can tell it that, okay, this is GPS component, it's going to need a UART, and it also wants to have the operating system as well. So we then have to add those additional components to our project, and then we can go off and have a successfully configured platform. So this makes setting up a project easier and easier, and you don't start to make silly mistakes. Once we've defined our software components, we can reuse them on any future projects, but all of the elements that we've used to create those projects are available as safety certified components as well. So things like the RTOS, the event recorder, the CMSIS core, and the C library are all available as certified components. So if you're doing a safety project, you can use these. The CMSIS drivers you would need to certify for yourself though as well. So now we have our application, we have our architecture, the different layers, the reusable components, CMSIS drivers and custom drivers. So we can configure it, we can expand the debugger, we can improve our software quality with software test, we can use additional static analyzers as well. Once we're all happy with that, we can generate packs for code reuse. So this, if you start to think about how you're going to use a software architecture on future projects, once you've defined it and you start adopting it, the gains increase over time. So the more components you've got, the more reuse you get, the faster you can develop. So we'll be presenting a number of projects and papers on this in the future. So if it's something that you are interested in, let us know in the survey at the end, and we'll make sure to keep you up to date. So thank you for your time today. I hope that was useful. And again, we'll see you for our next webinar.